Okay, so hello everyone. I'm super excited to be here. My name is Denis. I am a developer advocate at Couchbase. And today we are going to talk about the hidden costs of poor database access. For those who never heard about Couchbase before, Couchbase is a NoSQL database, fairly similar to MongoDB and Redis, but Couchbase is designed for more critical scenarios when you need high scalability. That's where people usually go to Couchbase because the key thing in Couchbase is actually performance at scale. But today we are going to talk a little bit about databases in general and some of the issues with it. But I would like to start with a small disclaimer here. I think as software developers, we are getting paid to build good enough software. What I mean by that is, well, our stakeholders, they are interested in a feature that is good enough for a short or mid-term. So you don't need to make the best feature ever or the most performant feature ever. And it's okay to trade off some performance if you get productivity back, right? And you don't have to feel guilty. I know quite often when you are building a software, we know that, okay, if I build a new method, this will be faster, but I don't have time, or it will take a few hours, so let's just reuse some that already exist. And this is totally fine. You are getting productivity, you gave up on some performance, but we are getting productivity back. What really makes me sad is when we actually trade off performance for nothing. And that's really a little bit about what this talk is about. From 10,000 feet, we can basically say that our application has three main components. Of course, the front-end, back-end, and the database. And I always wanted to be the performance guy. So whenever everything is on fire, everything is super slow, the company could call me and say, hey, Dennis, can you please help us and make everything run faster? And I could come over and say, oh, yeah, let's change some JVM parameters here, and boom, everything will run faster. But in reality, what happened with me was I was expending most of the time in the database, basically creating indexes and trying to understand, okay, what's going on, what can we do to improve here? And yeah, I got it. The databases are, in fact, the bottleneck of most applications. That's totally fine. But what you can do is very limited if you have a lot of bad practice in your code. So if you build a whole application with a lot of bad practice, there's nothing much else you can do in the database itself. And right now, things are getting even more complicated because we already have a lot of good materials out there saying, hey, here's some good practice, don't do this, don't do that. So when you go to a company and say, okay, what's going on, why your application is slow, you never find something like, okay, some method that loads 10,000 objects to memory and then use 3 of them. It is, in fact, the reason why the application is slow is a series of small problems that at some point they add up and make everything run slow. Let's give a simple example here. So let's say you have your REST API, and you have here your username, and you have your username in the path, of course. And then you have your mappings. I'm a Java guy, so most of the examples will be in Java, but I try to make this more as generic as possible. But here you have a auto-generated ID, and we have the username, and we basically query the username because that's what we get from the path of the URL. To be honest, nothing really wrong here. However, yeah, in most databases, this will take like around 3 milliseconds to run, I would say, in an average database with with a reasonable number of rows. And that's totally okay, but, well, there is nothing faster and cheaper than loading data by the ID. So why not make the username the ID of your table? The reason why there's such a big difference is because when you're querying the data by the ID, you skip a lot of steps internally in the database. You are basically using a key, the database as a key value store, and any key value store will pretty much have the same performance. It will be super fast. And instead of getting the data, the user in milliseconds, you can get the same data in microseconds now. However, you can say, okay, no, in my use case, I want to allow user to change the username, right? And that's why I can make my username the username the ID. That's fine. But what about other entities then? What about, like, let's say address? If you can only have one address in your application, why not make the ID of the address the ID of the user plus something? So whenever you need to get back the user, the address of the user, you don't need to query the database. You can go there and get straight the ID. And this will make the application much faster. And of course, like the user, you are gonna load the user thousands of times pretty much in every single request. I mean, a few times every single request, and that's important to you. You have to make this getting this data back as fast as possible. So this is just an example. If you are familiar with any key value store, that's pretty much how you use key value stores. You basically concatenate IDs and you go there, because in key value stores you can't query the database, or the query is super difficult. So you basically use this strategy of guessable IDs to get the data back. Of course, this could be considered a security flaw. OWASP, for instance, say, okay, you should not have guessable IDs. But in some cases, this is totally fine. If you have the proper security layer in your system, making this kind of change is something that will give you a lot of performance. Another common issue is select star. What's wrong with select star? Essentially nothing, right? It's all right to use select star. However, when you use select star, you are basically not getting the most out of your indexes, because there's not any space left for the database to optimize. In database, we have some databases have something called cover and partial indexes. So cover indexes is basically when you can say, okay, I want to create this index here, and I want to store the username, the name, and the language in the index. So when you write a query that is querying the same username, name, and language, the database can get the data out from the index and return that to you. If you have select star, the database has to go to the index, get the data there, and fetch more data from the table. And this might not make a big difference when you are in a small scale, but on a large volume of data, that makes a lot of a big difference. And we also have partial indexes, which is, okay, I'm only interested in active users. And you can make this, if you have a lot of inactive users, you can make your indexes much smaller and consequently much faster.
But don't you need a full table access when you don't have pro users? Equals true?
Sorry?
There, pro user is not part of the index. You need a full table scan anyway.
That's fine, because, no, good question. So in this case here, the subset of active users is bigger than the subset of pro users. So the database is smart enough to say, okay, this example here, the index is, the index that I have is bigger than this subset here. And that's why you don't need to have the exact index for each query. The database is good enough to say, okay, I can still use this index here. But we can talk more afterwards. Preparing statements. So prepared statements is something quite important also, because I don't know if you guys ever stop to think about this, but whenever you execute a query in the database has to create a query plan. And this query plan is something, basically, is how the database is going to execute the query internally. Here is an example, of course, in Couchbase, but pretty much if you execute your query with this explain keyword in MySQL, Postgres, or whatever, you will get the whole query plan and how the database will execute this query. In this case here, for instance, you can even notice some problems with your query. In this case, you can see how the query is being executed, and we are not using any indexes, and that's why the query is running slow. However, the problem with query plans is, as you have to generate a query plan for every single request, and this takes a few microseconds, but you're executing millions of queries in the database, that consumes some CPU in the database. And CPU in the database is definitely something they want to save. So what we can do in the code is use this thing called preparement statements. So what preparement statements do is basically say to the database, hey database, I'm going to execute this query quite often, so please, you can cache the query plan somewhere, and whenever you see this query, you can just reuse the same query plan. And this will allow you to also save some CPU in the database and makes everything be executed faster because you are skipping some steps internally in the database. Well, next, blocking versus non-blocking API calls. How many of you are familiar with reactive programming? Ah, that's awesome. So, for those who never heard about it before, in a traditional database access, we have our application, and our application makes some call to the database. And what we do is basically our application or our backend waits for like a few milliseconds or 30 milliseconds, whatever. And at some point, we receive the response back from the database. The problem here is, while we were waiting for the response from the database, this thread was consuming CPU, memory, energy, and doing nothing other than waiting the response from the database. And that's a pure waste of resources, right? So that's how we used to do a lot in the past. And now, reactive programming is nothing new, but a lot of frameworks get popular in the last 2 years, I would say. And put it simply, in a reactive approach, you basically make a request to the database. For instance, your application gets suspended, and you release all the memory, CPU, and other stuff, and other things can get processed in the meantime. And once you get the response back, your code is called again, and then you continue executing whatever you are doing. So in this kind of approach, you can release, whenever you have to wait for something, you can release all the resources, something else has a chance to be executed, and then once you have the resource back, your code continues executing. And when you compare this approach to the standard blocking one, the difference is quite impressive. You can literally, the bigger is the delay, the better it is to use a reactive approach here. So this is something that you can even run less servers with it. So for instance, if you're running on 10 servers, with reactive programming, you can even use 3 servers in your application, because that's such a big improvement right now. And I think this is one of the things that will get super popular in the next 2 years, potentially. It's hard to find a benchmark of the performance before and after, but there is a super cool talk from the Zoo's journey to non-blocking. That's basically the topic of the talk. It is already 2 years old. But basically, Zoo, in this framework, Zoo is an API gateway from Netflix. They basically make a comparison of what's the performance difference before and after re-implementing everything to be reactive. And then they didn't even had a lot of database activity because they are just a proxy, right? And then still got 20% of increase in performance. And that's a lot. That's just a few things you can do in your code to get 20% of increase. We also need to talk a little bit about joins, right? This is, whenever we talk about joins in databases, this is where people get, like, you get a lot of discussions. Essentially, databases were designed to rely on joins, and they have been doing this quite well, to be honest. Of course, if you don't have your proper indexes, on a DBM4 large with 1 million rows each column, a join will cost you something around like 97 milliseconds. However, if you have the proper indexes, it will cost you less than a millisecond. So it will be super fast. Of course, if you're bringing a lot of data from the, like, let's say you're bringing your like you are loading, like, let's say 50 users from the database with all the related entities, this will add up and have some impact, but it's still not that bad. And I would say that because of this, joins, a properly set up environment with joins is good enough. Is super fast. And that's one of the reasons why the normalization in relational databases doesn't worth that much. So if I have a shopping cart and a shopping cart item, does it really worth to store the name of the item in the shopping cart item? Yeah, if for each product to join with a table product, I'm spending just less than a millisecond. Well, it's easier to just get the product back, join with the product table, and get the data back. So the normalization, apart from a few scenarios, doesn't work that much because joins are faster. For me, the real problem with joins is they are super annoying. So if you are old enough, you probably remember how our DAO classes in the past used to have like 13,000 lines, because we had to, like, just to bring the user back, you have to join the user with table of security roles, the table of preference, the table of address, and all the stuff. And you have to make these huge classes that are just parsing from relational to object, and from object to relational. And that's terrible, right? Because, again, we can give up some performance if you get productivity back. And that's when a lot of these ORM solutions appeared, right? And they are really great because you can get a lot more productivity. You don't need to write every single query. You have this abstraction query language that is automatically convert everything to SQL. But there is some overhead, of course, of using ORMs, because now we have one extra layer. We also have to map relationships, and usually there is a lot of tricks there. So and traps, because for instance, in Java, if you create like a one-to-many relationship, if you map it wrongly, it will generate unnecessary junction tables. For instance, here we have a post comment, and post comment. This table in the middle is not necessary. And the reason why this was generated was because we did a wrong mapping in the code. And quite often we see like the first answer on Stack Overflow is a wrong answer. So you really have to check what's going on, what's happening in the database itself. And of course, because you don't know that this table is being generated, quite often you don't create the proper indexes, and that's when everything starts getting slow. And of course, one of the problems also with this kind of approach is we quite often overfetch data, right? Because you map relationships to be eager, and then when you get the user back, you probably get much more data than you need. So ORMs are good, but we as developers, we have been trying to make the database as generic as possible, and we never double check what are the actual queries being generated in the database. And that's one of the issues why one of the reasons why we have so many issues with ORMs in general. Okay, and maybe you can say, okay, now this is the eager, right? What if I change everything to be lazy then? I can change my relationships to be lazy. And in this case here, I have a building, and I have companies, and if I acquire all the buildings and I want to iterate to the companies, what will happen is we will have this first query being executed in the database to bring all the buildings, but every time I call in my code get companies, Hibernate under the hood will execute a new query. And that's again, because instead of bringing all together, this will be super slow again, because in every time you are iterating you call get companies, you are basically executing a new query there. There is this, if you're a Java guy, there is a super good book that talks a lot about those issues called High Performance Java Persistence. This is the guy who is basically responsible for the Hibernate framework. But the problem for me is, okay, in a relational, if I execute pure SQL, I can in theory get more performance, but I will be less productive. I will have less productivity. But if I use an ORM, I can get more productivity but less performance in general. And the issue is why do I have to choose? Why can't I have both? And the root cause of this issue is something much bigger. The problem is something called impedance mismatch. So if you think about it, the way we deal with code, with data in the code, is completely different than the way we store data in the database. Basically, when the database were created in the 70s, yeah, that makes a lot of sense to store everything in tables and rows, right? However, that has been the same for the past 30, 35, 40 years. And in the other side, in our application, we completely changed the way we code, but we are still trying to store data in tables. And that doesn't make sense. What their ORM's frameworks are trying to do is basically, okay, it's a small breach that tries to make this friction less apparent. So that's the biggest issue here. We store data in a way, we deal with data in your code in the different way that we store in the database. This criticism in SQL is not something new. Here's a blog post from 2004, already saying, hey, we need to evolve this table, this relational model. And that's why when you go to, let's say, NoSQL databases, quite often, they use different formats. Doesn't matter, you can use JSON, you can use XML, you can use YAML, but the structure is usually some kind of hierarchical data. So you can have nested entities or arrays and all this kind of stuff, because this is exactly the same way we deal with data in your code. And translating from an object to a JSON is a super simple operation, right? But let's step back a little bit and talk about scaling a database, a relational database. If a relational database is fine for you, you're not having any issues with performance, you are totally fine, live your life and be happy. However, at some point, what happens with databases is, okay, I need to scale my database. And what do? You add more memory, add more CPU, and that's it. And then if your company continues growing, you get more users, things start getting slow again, and what do? Boom. You basically buy an even bigger machine. And the problem is, we are living in an era where we are trying to build distributed systems. That's why microservices is getting so popular. And we'll say, okay, we need to break the monolith and create smaller applications. But the database is pretty much the same thing. We are only scaling up. And there's many reasons why, but let's just pick one example. In a relational model, your user data is distributed between multiple tables. So you have the user table with preference, a table with your user, a table with roles. And when you have this running in multiple servers, there is a big chance that you have to, when you need to load the user back, you have a cross-node joins. And that will be super slow. And that's why most of the relational database, the design of the relational database itself was created with a rule that, okay, this will run in a single machine. And if I want to scale out, I have to use a totally different approach. And that's why, even though relational databases have been there for like 20 years, the way you scale a relational database is pretty much the same. You just make the machine bigger. And the problem is, if in the past, let's say in 2006, 2008, just Google and Amazon had problems with scalability, now we even have startups having those issues, right? Because data is growing much faster than our hardware capacity. Think about Pokemon Go, for instance, which is already like 4 or 5 years old. They basically went from 0 to almost 300 million users in a month and a half. And that's some of the use cases, like gaming, for instance, is a field where scaling is super important because you have this bus, and then you have like a really short period of time where you can get all your revenue from this game, and then people stop playing, or another new game is launched, and you lose the traffic. So scaling out in gaming, for instance, is something super important. Cool. So in general, if you say, okay, this is how data in JSON looks like. So this is an example of a route. So from Chicago to Columbus, for instance. And you see here, yes, I still have the airline ID, so I can have foreign keys, I can do joins. And here I also have the schedule, because the schedule only makes sense to exist inside a route, right? Like I can have doesn't make sense to have a schedule in another document, because the context only makes sense when it is inside a JSON. Cool. So yeah, having this kind of hierarchical data is something valuable. We could have also some kind of hierarchical data in a relational database. But then we have another problem, which is how do we query this data, right? Because now it's not flat data anymore, so SQL doesn't work. And what happened in the past is a lot of super smart people create new languages, and to be honest, some of them are mind-blowing. But we all like SQL, and it's not just developers. Like even in academy, people still like SQL, and whenever you see a totally different language, you say, okay, I don't like this that much. I want to stay with this. So some folks from University of San Diego, they saw this and say, hey, okay, so we need to improve this relational model. We need to store hierarchical data and databases in order to be able to scale. But people like SQL. So what are the minimal changes we can do in SQL to make it work with with hierarchical data? And they create in 2015 they published a paper called SQL++, the query language, which was basically a set of some extension of SQL to say, okay, if we add those keywords in SQL, this will be good enough to work with hierarchical data. And then some other universities actually joined the game and they started working with SQL. And even the father of SQL itself, Don Chamberlain, the guy who created SQL, saw, okay, this is interesting. And he created a book called SQL++ for SQL users. And back then, Couchbase saw this and said, okay, we were just a key value store. And we were like, okay, this is interesting for you because we already store data as JSON, and we want to give the chance for users to query this data. So we implemented this specification, and we came up with something called Anyone QL, or NQL. And this has been like 4 years since we implemented Nico, and it's working really great for us. But let's show you a few examples here. So this is an example of SQL, right? So you have select star, select foo bar from my table. And this is an example in SQL++. It's pretty much the same thing. In fact, the only difference here is that we are querying a JSON data. And if you squint really hard in this part here, you actually see a table here, like multiple, a simple table. However, SQL++ has some extra powers, I would say. So for instance, let's say I want to select the city of the user here. Right? I have a JSON structure, and I want to select the city of the user. What I can do is just use select address.city, and then I'm getting the city of the user. And okay, I know what you guys are thinking, right? This is kind of old news because we have been doing this for ages in Java persistent query language and some other ORM query languages. That's true, but now you are doing this native. It is natively supported by the database. Some other example. Let's say I want to select the second favorite food of each user. I can do something like favorite foods and pass the index. Right? Super simple. What if I want to select all the users that have pizza as a favorite food? And I can do something like, okay, select where any favorite food satisfies f equals to pizza. Simple as that. I mean, even sound obvious, right? Like, makes a lot of sense. You guys had no experience with SQL++ in the past, and you can clearly understand what's going on here. We have some other stuff here. Let's say I want to promote favorite foods. So favorite foods is a nested entity. I want to unnest this entity. I want to bring this entity a layer above. So what I can do is actually use the word unnest. And I can, if I use this query, I can get like Matt, pizza Matt, cheesecake Matt, and Dennis Matt. So this is pretty much like a self-join, I would say. It's like a join with the document itself, but you're promoting this a layer above. And guess what? This is also backwards compatible. So I can do joins, I can do otherwise, I can do groups, I can do average, I can do maximum, whatever you are used to in SQL, you can do here, but with some extra power. And of course, our implementation, for instance, has been, we have thousands of, I mean, not thousands, but a few dozens of keywords already. And it's really, I mean, we would need a whole a session just to go over them. But the good thing is, we are not the only ones now. AsterixDB, Apache Drill, Hierarchical, which is AWS, a new AWS database, they're all already following this pattern, which is super cool. This is one thing that we really want to push because the relational model has to evolve. We have to, okay, tables are fine at a small scale, but this model doesn't work when you have to distributed systems. Think even about like transactions, right? Let's say I want to insert a new user. And to insert a new user, I have to insert in maybe data in 6, 7 different tables. So in a relational database, I have to, when I insert a user, I have to start the transaction, insert data in all those 6, 7 tables, and then commit the transaction. When you have data as JSON, for instance, which is a hierarchical data, and everything is not a single document, I don't even need a transaction because the update, the insert is atomic, so it's all or nothing. So I can just insert data, and if something fails, I will get back an exception. So I don't need to start a transaction, and this helps you to get rid of all the overhead of a transaction. And without the transactions, everything your insert can be much faster. So, yeah, if you are aware, if you're a SQL guy, you probably remember that SQL 2016, they introduced support for JSON. We see some support on Postgres, on MySQL, and some other database for JSON. But that is a totally different scenario. They are just to say, okay, you are using a relational database and you need to store some JSON, you need to query some stuff. This is something you could use, but this is just, okay, I implement this extra use case here. It's not, SQL++ is a whole different approach. And in fact, if you see how difficult it is to query data in those databases, when querying JSON data in those databases, you say, okay, SQL++ is something far better. Even Don Chamberlain, again, the father of SQL, he posted an article comparing SQL++ with SQL 2016, and the conclusion is basically, okay, this is different scenarios. They are totally different scenarios. SQL 2016 is just, okay, I have some basic JSON data I need to store, I need to make some basic queries. And SQL++ is a whole different approach where we are evolving the model of the database itself. Well, the reason why I talked about hierarchical data and SQL++ is because when we have this implemented in our databases, we can actually get rid of all the ORMs because we don't have an object relation mapping anymore. So the ORMs will become something else, like maybe we can call persistence abstraction layer or something else, which is just, okay, making my code less verbose, but you can write SQL++ queries and they will look very similar to what we already do with ORM today. So we can get rid of this workaround called ORMs, and we can go back and write directly to the database again and have nearly the same productivity. But this time, we know exactly what's going on. Right? We don't have any traps in the middle because we don't know how the ORM was implemented or how this annotation will affect the performance of your application. So I do think that this is something that we have to fix in the next few years. I am almost done here. So some key takeaways for you guys. First, it's okay to trade off performance to productivity. As long as you are getting productivity back, it's a way to give up on some performance. ORMs, they are awesome. Yes, we couldn't. It's hard to think any application nowadays that doesn't use an ORM. But as developers, we still have to double check everything that's being generated. Because quite often, the reason why they are slow is because you are not aware of what's going on under the hood, and then you get some unexpected behavior and everything gets super slow. And the last thing is, okay, we knew for quite a long time that the relational model wasn't good enough, but we didn't have any options, right? It takes a long time usually to build a database. I would say that databases are pretty much like airplane engines. It takes like 10 years to create a reliable database with all the basic features you need. And now we already have some options there. We have some implementations, and even though you don't want, even if you don't want to use those databases, it's totally fine. But it's important for you to know that the language, the model, has to change, has to evolve. And guess what? We developers are the ones driving the change in the software industry. And if you pressure databases, they will eventually implement hierarchical structures, they will support this kind of thing, and you can get rid of extra overhead in your application. So this is pretty much what I have. If you like this talk, please don't forget to rate this session. And yeah, if you have any questions, I will be happy to answer.